So Newton's third law has to do with equal and opposite reaction. Okay, every single force comes in a pair. So for every action, there is an equal and opposite reaction. How many of you have heard that phrase before? Right, that's Newton's third law. So for every action, there's an equal and opposite reaction. So if I exert a force of A on B, right, if I push on something, if I push on an object, I'm exerting a force of A on B. That object exerting the exact same force back at me, but in the opposite direction. Okay, so if I exert a force, if I push on something, that object is technically pushing back or exerting a force back on me exactly the same magnitude, but in the opposite direction. So that's what the negative indicates there, that we're looking at it going in the opposite direction. Okay, these are called interaction forces or reaction forces. You can see that here they are of equal magnitude, but they're in opposite directions. Okay, so if I push on somebody and they start backing away, I kind of have to react backwards too. Have you noticed that? If you'll start pushing on somebody, you both kind of fall backwards. Okay? What happens is that when they are resisting, or that when they are having a force exerted on them, they're exerting that same force back on you. Okay? And if you don't resist with enough force, you'll start to move backward as well. Okay? What it means, how we can specifically solve for it a little bit better. So I need you to get your textbooks out, and I want you to read page 105. It has some more explanations about the tension force. You can follow along on page 106 if you want. We're going to do the whole problem together as a class anyway. Okay, so get written down what you need to. If you want to follow along or look at the picture of it, you can see that on page 106. It's example problem number 4. But we're going to work through the whole problem as a class anyway, so that's up to you if you want to follow along in the book. Let's start this problem with our free body diagram. Alright, so let's start with our free body diagram. This object, or this bucket, we'll put over here on the left-hand side. Give me one force that's acting on it. Nate G, tell me one force that's acting on it. FT. Okay, good. And is it going which direction, up or down? Up. Good. Our tension force is going up because that force due to tension, or the rope, is trying to keep that bucket upright, right? It's trying to lift it. Elizabeth, give me one more force. Which one? Okay, good. And it's going which direction? Down. Okay. Are those the only two forces we have acting on our object? Yeah. We're not moving it side to side at all, so we don't have any horizontal forces we need to look at. So in our problem, we were given mass, right? Mass is equal to 50 kilograms. We were also given a maximum tension that we can withhold, okay? This rope has the ability to withstand 525 newtons of tension. So the bucket started at rest, and after it's lifted 3 meters, it's moving at 3 meters per second. If acceleration is constant, is the rope in danger of breaking? So our goal here is to see if the tension in this particular example, is it going to exceed the maximum tension that this rope can withstand, or is it going to be below that? Right? If it's below the amount of tension that this rope can withstand, it's not going to be in danger of breaking. If our tension force is higher than 525 newtons, then we're going to have to be careful. The rope's going to be in danger of breaking. Okay, so we're going to use that 525 as a comparison. That's not going to equal our force of tension. It's going to be a comparison number. Okay, so let's go ahead and use our kinematics here to solve for acceleration. Right? We don't know our overall acceleration of our object, do we? But we know our distance final, and we know our velocity final, okay, and our velocity initial. So our distance final is equal to 3 meters. Our velocity final is equal to 3 meters per second. What's our initial velocity? 0. Yeah, because it starts from rest. We start to lift the bucket up. Now, what equation can we use to solve for our acceleration? Yeah, Vf squared equals Vi squared. So we'll use this equation, Vf squared equals Vi squared plus 2a delta d. So Vf squared is 3. All right, and is our object accelerating in the upward direction or the downward direction? Upward, right? We're lifting this bucket upward, so our acceleration is in the upward direction. Okay, do we all agree with that? Did I do the math right? 1.5, okay. So now let's go ahead and look at our F net equation here before we can start doing some substitutions. F net is equal to upward forces minus downward. So that means we're going to take F sub t minus F sub g. What substitutions can we make here? F sub g equals what? Mass times acceleration due to gravity. Mass times little g, those are different things. Little g, what can we substitute in for F net? MA. And we're solving here for our tension force, so that gets to stay the same. We're solving for our tension force. So now we can start plugging in what numbers we have. We have 50 kilograms for our mass. We have our acceleration equal to 1.5. Ft is what we're solving for. We're solving for that tension force. G is always 9.8. How do I get F sub t by itself here? We're going to add that 490 over to the 75. Add that over. So what this means is that in our system, if we accelerate, if we lift that bucket up with a 1.5 meters per second acceleration, our tension in our string is 565 newtons. Is our rope going to break? Yes. Yes, our rope will break. So if we answer our question correctly, the rope is in danger of breaking. Yes, it is, because it exceeds 525 newtons. It's higher than or greater than 525 newtons. Okay? All right, what questions do we have here? Remember that drawing your free body diagram and writing this equation is very, very important. Okay? When we have something that's greater than just a net force, when we have something that we have to work with, we have more than just a net force, we've got to make sure that we're putting this equation in and we're substituting what we can. Okay, F sub net, that's your overall sum of forces, right? Anytime we have the net of something, it's the overall. And that can always be mass times acceleration. F sub g, what's our key word for F sub g? When we see this word, we should always think F sub g. What is it? Kind of gravity. But when we see the word weight, anytime we see the word weight or weighs, we have to think F sub g, which is equal to mass times 9.8. Mass times 9.8 equals force due to gravity. All right, so 565 newtons, so our answer is yes. It's in danger of breaking. All right, any questions there? Yeah?
F sub g is...
So we're going to review some of our forces and we're going to dive into them a little bit deeper. So we're going to look at our normal force here. This is a diagram that's on page 107 if you want to take a look at it a little bit closer. But we're going to solve for each of these situations. Okay, we're going to solve what our normal force is in each of these situations. So let's start with just this first. We're going to start with just this first object. Okay, when our box is at rest. Okay, so we're just looking at this first diagram. We've got a normal force and we've got a gravitational force acting on this object. So I'll draw it a little bit bigger here so we can see it. Normal force and gravitational force. Okay? Let's say that the mass of this box in every example, mass is equal to 20 kilograms. Okay? Are we on the same page? So let's talk about just when this object is at rest, we want to find what the normal force is equal to. Okay? So we've got our free body diagram. We're going to set up our F net equation. What's our F net equation? What minus what? You need to be doing this with me. There's no reason that you shouldn't be participating. Okay? What's our F net equation? Good. Fn minus F sub g. Perfect. Is our box accelerating upward? In this? Is it moving at all? No, which means F net is equal to what? 0. F net's equal to 0. It's not accelerating in the upward direction. So it's equal to 0. So anytime our object is at rest in the vertical direction, we know it's not moving in the vertical direction, net force has to be 0, which means F sub g is equal to F sub n. So that's how we can go about solving for our normal force a lot of the time. If we know that F sub g is equal to F sub n, what do we know about F sub g? Mass times gravity. Okay, so I'm going to take mass times gravity to equal my normal force. Which means that the normal force in our first problem here is equal to 20 times 9.8. .196 newtons. Okay. So I need you to start recognizing the fact that this object's not moving in the vertical direction at all. It's not accelerating, which means our upward forces have to equal our downward forces. Okay, upward forces have to equal your downward forces because it's not moving, it's not accelerating in the vertical direction. This one's just sitting there. We're not even doing anything special with it. So our normal force has to equal our gravitational force. We know that the gravitational force, or F sub g, is always equal to mass times gravity. So that's going to be how we solve for normal force a lot of the time, right? If those two are equal to each other, if the system's at rest vertically, we've got to know that those two, that's how we can solve for that, taking mass times gravity to equal our normal force. Okay? All right, so in our middle problem, we're exerting an upward force. We're attempting to lift this box off the table. We're trying to lift it, but we're not accomplishing that goal, right? It's still sitting on the table. We're just exerting an upward force to attempt to lift it, Okay, so let's look at our free body diagram here a little bit closer. In our free body diagram, we've got our force due to gravity. We've got our normal force. And we've also got an applied force in the upward direction, right? Because we're attempting to lift that box upward. So we've got two upward forces here. And the way we do that if we have two is we add them one right on top of the other. Can you see that red okay? Okay. You can call that upward force force applied. You could call it force tension because they're technically lifting by a rope. Either way is fine. This one, it doesn't really make a difference, okay? But I need you to see that we've got two upward forces here. Okay, we're trying to lift that box off the table. It's not quite working. We're still at rest. Okay, so now let's set up our net force equation. All right, Vicki, what do you think? Can you tell me our net force equation? Upward forces minus downward. Plus what? Good. Plus normal. Perfect. Perfect. We're going to add together all of our upward forces. We're going to subtract out all of our downward forces. Okay, so anything that goes up, we add. It's in the positive direction. Anything that goes down, we subtract out. It's in the negative direction. Okay, so no matter how many forces you have acting here, we're going to put them all into that net force equation, either vertical or horizontal. Remember that we don't ever mix horizontal and vertical. Okay, we keep those separate. So here we only have vertical, so it's not a big deal, but I want you to keep that in mind. All right, so is our box moving in the upward direction? Is it accelerating in the upward direction? No, it's not. We're attempting to lift it. It's not getting off the table. We're kind of taking some pressure off the normal force. Okay, so our overall net force has to be equal to what? 0. Good. Because our box is still at rest. It's not moving. Okay, in our diagram, it gives us the value of our applied force, and that's equal to 50 newtons. We're solving for our normal force. What do we know about F sub g? Mass times gravity. Mass times gravity. So mass times gravity will take 20 kilograms times 9.8. So I'll move this over a little bit. And we get 0 is equal to 50 plus F sub n minus 196. So then on that side, we'll take 50 minus 196 and get F sub n minus 146. We move that 146 to the other side to get it equal to F sub n. That means that the normal force here is 146 newtons. So does it make sense here that in our second problem we've got a lesser or a smaller normal force than we do in our first problem? Does that conceptually make sense to you? I'm attempting to lift it, which means I'm taking some of the pressure off the surface. I'm counteracting gravity a little bit by myself, so the normal force doesn't have to work quite as hard. Does that make sense? I want you to see that so you can understand that whole conceptually, that why you're getting a smaller number in this equation is because we're taking some of that pressure off the normal force. We're attempting to lift it. We're working against gravity a little bit so that the normal force has to do less. It has to exert a lesser force. Okay? Any questions on that one? Yeah. The normal. Okay, so in this example, we're pushing down on the box, which means gravity's pulling down, and our applied force is going down as well. Okay, which means that our F net equation, Logan, can you give me our F net equation?
F net equals Fn minus Fg plus F applied.
Close, very close. F applied is still going in the downward direction, so we're still going to subtract. We're still going to subtract the F applied because it's going in the downward direction. Very close. Okay, if you really, really wanted to put this in parentheses, you could add them, but I don't recommend getting into that. Okay, I just take all of our upward forces, subtract out every downward force. Okay, that way you get used to that. So questions about where that equation came from. One upward force, which is the normal force, and two downward forces, which were gravity and our applied force. All right, is our box accelerating upward? Is it moving in the upward direction? No, which means F net's equal to 0. Good. F sub n is what we're solving for. What can we do with F sub g? Mass times gravity. Always, always, always when we have F sub g, we're going to take mass times gravity. So I'm going to go ahead and plug that in. 20 times 9.8. And our force applied here in the downward direction, they told us was 50. So that means when we do the math here and we rearrange our equation, I got a normal force equal to 246 newtons. All right, because I took negative 196 minus 50, and I got 0 equals F sub n minus 246. I add that 246 to the other side, which gives me a normal force equal to 246 newtons. Try to condense this into your own words, right? You don't need to copy this problem word for word. Condense it down in your own words and in your notes. All right, so the easiest way, or the most applicable way I think you can think about problems like this is if you're trying to lift something really heavy, if you're trying to lift something on a rope that's really heavy and you pull too fast, what happens to the rope? It breaks. Like if you're going fishing and you have a line that's not built for that much and you have a big fish and you try to set the line, the rope's going to break, right? The string or the whatever, the line is going to break. That's what we're looking for here. We're going to find out how fast we can pull that rope up, how fast can we lift that bucket without the cable breaking or without the string breaking. Okay, we're trying to find what's the maximum acceleration that we can expend in order for this rope not to break. Okay, so let's start with our free body diagram here. How many forces do we have on our object? Just 2. Good, very good. What's one? Aiden, give me one. FT, okay, good. Aiden, give me the other one.
Gravity.
Good. F sub G, very good. Okay, technically, which of those forces should be longer? F of T, right? Because we want to lift it upward, so we want our net force to be in the upward direction. Not a huge deal when we draw our free body diagram. I just want you to start thinking that way, okay? So our net force equation looks like this. F net equals force of tension minus force due to gravity. Okay, our upward forces minus our downward forces. Here we're trying to solve for the acceleration. Right? We're trying to solve for the maximum acceleration that we can lift that without our tension breaking. So our tension force we already have here. We have our tension force. What's the value of our tension force? 450. What about F sub G? What do we know about F sub G? What can we substitute there? Good. 9.8 times what?
40.
42 times 9.8. That's mass times gravity. And F net, we know we can substitute in what? M times A. M times A. We know our mass is 42. We know we're solving here for acceleration. So we want to leave the A by itself. All right, so we were solving for acceleration. That has to tell you that, okay, I need to substitute mass times acceleration here. Otherwise, I don't have acceleration anywhere in my problem, right? I have to substitute that. We were given our maximum tension force, which means this is the maximum acceleration that it could go. Okay, the maximum acceleration that it could go. We know mass times gravity is equal to F sub g, is equal to our gravitational force. We know that force of tension was given to us in our problem, so our maximum acceleration is 0.914 meters per second squared. Okay, so as you're standing on a scale, remember the scale's job is to exert a force upward on you. That will be its reading. So you can call it the normal force, you could call it F sub scale, you could call it F sub spring. Whatever you would like to is fine. I would just pick one and try to be consistent. I usually pick the normal force just because it's something that we're used to hearing. Okay, you could also name it F sub scale if you wanted to. Okay, but this is our free body diagram here for our dog standing in our elevator. Okay? So what's our next step? We've got a free body diagram. What's our next step? Set up our equation. So what is it, Alex? What's our F net equation?
F net equals MA plus MB F scale plus.
F scale.
Plus.
Okay. Nope. Not plus, because F scale's going up, so FG has to be going.
Oh, so you're subtracting.
Yep. We always take our upward forces minus our downward forces. So F scale or F normal, whatever you want to name it as, is going in the upward direction, so that stays positive. F gravity, or force due to gravity, is going down, so it's got to be negative. Okay? Here, our 10 kilograms tells us our mass, and our 2 meters per second tells us our acceleration. So we need to substitute F net for what? M times A. Good. We're solving for F scale. We know that F sub g is equal to mass times gravity. Here's something that we need to really pay attention to. We're accelerating downward, which means our acceleration needs to be -2. Okay, so I'm going to move my equation down to the bottom here. So we're going to take 10 kilograms times -2 equals F sub scale minus 10 times 9.8. Okay, 2 kilogram bowling ball is sitting on a table. If someone exerts a 12 Newton force to lift the ball at constant velocity, what will the normal force be? Okay, F net is equal to F normal plus F applied minus F sub g. You could call it F lift if you want to. This one you could change the name. But essentially, if we're attempting to lift something but we're not getting it off the table, our F net has to be 0. Okay, that was a part that tripped some people up. Some people left out the F applied altogether. Okay, but we've got to have all three of those forces in there. So upward forces have to equal downward, and we should have gotten 7.6 newtons for our normal. Okay, so I want to see your free body diagram. I want to see the net force equation. We've got to think, is this box going to be accelerating horizontally or vertically? What do we think? Horizontally. That means we still draw the vertical forces in our free body diagram, but they don't go into our net force equation. We do not mix horizontal and vertical forces. Here we're only looking horizontally. Alright, so here we're asked two different questions. We're asked to find our normal force, which is vertical, and we're asked to find our horizontal acceleration, which is horizontal. So you have two different net force equations you need to go about using here. You've got to do two different ones. You can't solve for both of these in the same net force equation. How many of you got that for your normal force? Excellent. Excellent. All right, now let's look at horizontal. If you're still working, great. Keep going. Okay, I'm just going to put it up here if you're stuck or if you're not quite sure.